This material does not really have a life of its own. This is not something that is going to pull a lot of people in off the street to learn about. So we're going to go through in hopefully less than tortuous fashion and discuss soils and soil and water management. And we'll key this in very closely to the learning objectives in the National CCA exam. There will be a couple things on the state exam that may be a little bit different, but for the most part, I think you're going to find that most of the material that I present for you today is going to be pretty applicable to that exam. And we'll go ahead and get started on that. I've divided this up into several different sections. We're going to talk about basic soil properties that we can measure and how they might affect the way a soil performs from an agricultural sense. Talk about soil, water, and drainage. Get in a little bit in plant water use, how the plant uses water, how the soil stores water. Talk about soil conservation, and finally tie this in with tillage and a little bit about compaction. I've got a small little 2-slide section at the end, which was not worthy enough to put up here, that appears on some of the exams, dealing with saline and sodic soils. So this is going to be the main thing we're going to do today, and not only do I take questions, I encourage them, because typically if you're befuddled or confused, you're a representative of most of the folks around you. So if you have a question, go ahead and we'll get this on tape. Basic soil properties that we're going to talk about, perhaps ad nauseum. We're going to talk about these quite a bit. Soil texture, soil structure, and soil organic matter. And you undoubtedly will find questions from each of these areas on the exam that you take. Soil texture, for all intents and purposes, is an unchangeable property. We have a given texture of a soil out there. We're not going to influence it by any kind of management. It's the kind of deal where you just play the hand that's dealt you. Okay? Soil texture is an unchangeable property. We can measure soil texture. All it is the percentage of sand, silt, and clay, the so-called soil separates, that are going to determine what our soil texture is. Gravel may be considered in some areas. We don't have a lot of gravel in our surface soils in Illinois. Gravel is not specifically considered when we determine soil texture. So what we do is separate out the gravel, measure the sand, silt, and clay. Does organic matter have anything to do with texture? Trick question in some cases. It may be associated with texture, but it has nothing to do with texture. Texture is simply sand, silt, and clay percentage. So when someone talks about, a layperson talks about a loamy soil, they might mean to say that it's dark or has organic matter. It has nothing to do with it. Loam refers to a soil texture. We use something called a textural triangle to determine what the texture of a soil is. By knowing the percent of sand, silt, and clay, we can go to a textural triangle, and we'll have a little practice at this, and determine what the soil texture is. Those of you that don't have a hobby, I highly recommend just taking some random numbers of sand, silt, and clay and determining soil texture at home at night. Wonderful hobby. Healthy for you, too. Okay, soil texture, why do we even care about it? Well, soil texture is going to key in or be inferential for a lot of different other soil properties. The texture is going to tell us a little bit about how a soil works with tillage, how a soil is going to respond in terms of water, how it drains, how much water it holds. A lot of these other properties are associated directly with texture. I want to tell you too, all of you, I see some are taking notes, some are listening intently, others are using another learning method that we've come to learn here recently, where the idea of the audio and the visual and everything coming at you all at once is too much, so you shut your eyes and just take this in on an audio version. But just go ahead and stick with that program. I'm with you. I'm still with you, and I'm still teaching to you. Okay, remember texture, sand, silt, and clay. We're going to take the gravel out. So we screen the gravel out. These are the largest particles. Sand, fairly large particles. They're visible to the naked eye. They're rough. They're gritty. Silt is a little bit smaller yet. We have a lot of silt in our topsoils throughout the Corn Belt. The silt was blown in after the glacial period through here thousands of years ago. The glaciers ground everything up like flour. That's the best way to talk about the consistency of silt. and things dried out, and the silt was blown and deposited all over the Midwest. In general, this material is called loess, and it is blown from the river valleys and thinned out as we move east. So oftentimes we get thick loess bluffs near our major rivers, and then the loess cap thins as we go east towards Indiana. And this really is what's given us our real good soils here. Clay, of course, is the smallest particle size. It's sticky, it holds a lot of water, it has a tremendous amount of surface area. 1 gram of clay has at least the surface area of a football field. Just think about that. And really, in your fertility section, you'll hear a lot about cation exchange capacity. The clay particles, the clay minerals, are what are mostly responsible, along with the organic matter, for holding our nutrients, our cationic or positively charged nutrients, against the flow of water. So these are really the real active, whereas sand are the inert types of particles. What we have here is this textural triangle, and for those of you listening at home, I'll try to talk about this without pointing to it. If you look on the lower axis, moving from right to left, you see the sand percentage from 0 to 100%. And the lines that emanate from the bottom of this graph head up in what's kind of a northwesterly direction, if you will, moving along. The silt line starts at the top of the triangle, moves down on the right side, going 0 to 100. The clay line starts in the lower left-hand corner at 0 and moves up to the apex of the triangle. So the sand, silt, and clay are always going to add up to 100%. Those of you that have some advanced mathematics, how many of the two particulate percentages do we need to know to determine the texture? 2. Outstanding. 2. Because if we have 2, we're going to find the intersection of those two lines, and those of you that actually not only are good at mathematics but got good grades in it, check your work. We can use the third particulate percentage to check and make sure that those 3 lines intersect. You understand with me now, if you go through the textural triangle and you land up with 3 different points that don't intersect, that you've made a big boo-boo here. Almost guaranteed you're going to have a question like this on the CCA exam, so you need to know how to use this particular thing. Let's work through a problem together as a group. Maybe it will encourage some bonding and so forth. You can continue on into the evening and come in here holding hands and have a big group hug tomorrow for our session. Okay, let's think about a soil that has 30% sand and 30% clay. Question 1, 30% sand, 30% clay. How much silt does it have? 40%. And you arrived at that mathematically by adding 30 and 30, summing them, and subtracting them from 100, and came up with the correct answer. Okay, let's move along the 30 line, starting with the sand, and come across with a 30 line from left to right on the clay. Where do we find ourselves? What textural class? Clay loam. This is a good group here. This is a very good group. Everyone here will surely pass this exam. Now let's check our work. Go up to the 40 line on silt. On silt, drop down towards the left corner, and sure enough, that intersects on clay loam. We're having so much fun, let's do just one more. Let's look at 60% sand and 30% clay. 60 and 30. How much silt we got? 10%. Okay, move up to 60 line on sand, across on the 30. Where do we come out? Sandy clay loam. Okay, so everyone's got this down pretty well. That's how you use the textural triangle. Don't get tricked by gravel, organic matter, any other kind of debacle. Sand, silt, and clay, move up and down the lines, find it. And I guess many of you can see at this point now why this is such a rewarding hobby. Imagine the satisfaction you get or continuously arriving at the correct answer. Okay, here are some collector item photographs here to give you a little bit of a sense of perhaps what some of these different textural classes look like. Again, I said that gravel was not considered in the actual textural class, but what it is put in as is a modifier. In this case, this is just a bunch of gravel, and if you look at the fine particles in there, they would come out to be loamy. Sandy loam, loam, silty clay, and clay. Most of our textures throughout the Corn Belt are going to be silt loam, which is not pictured here, somewhere between a loam and a silty clay loam. And I think you can see that as we get into the finer and finer textures, that what we're seeing is a little more tight structure, and that's the addition of clay that's causing that. We'll talk about structure in a little bit. So those are several different textural classes. Talk a little bit about structure. Okay, with texture now, we were talking about the percentage of soil separates adding up to 100, sand, silt, and clay to get our texture. We cannot change texture with any kind of management, okay, with tillage or anything like that. The particulates stay the same size. Structure is highly manageable, and a lot of our tillage operations, residue management, other things are going to affect the type of soil structure that we get. You'll be asked to identify some different structural units, perhaps. See an artist's rendition or a photo of these different things. There are several that you will need to identify, and these are in your learning objectives. Prismatic and columnar, blocky, platy, spheroidal, or granular. And you'll also be asked to discuss the benefits of these different structural units, what they might mean in terms of gas or water exchange or just crop production ability of the different soils. Again, the structural units are put together. Why? Because of different types of sand, silt, or clay, different amounts, different types, and the association with organic matter. If you go out to a nice pastured soil and dig up and grab the sod and shake it, you're going to see little small spheres of soil dangling from the roots. This is going to be crumb or spheroidal type structure found near the surface of the soil. As you go down into a soil, you're going to find different structural units. Some of this stuff would be blocky as we begin to go down. Granular near the surface or spheroidal, and blocky as we begin to go down. Show you a couple old collector item type photos. This is kind of a granular structure. These would be the blocky units. These are small units that you typically could break out of a subsoil in a humid or subhuman type environment like we're in here. Those of you that have had tile put in or had other chances to get out and dig around in the soil or see an excavated pit, if you went in with a knife and picked this stuff out, it would crumble out in little blocks. Angular and subangular simply means angular being sharp and subangular being somewhat rounded. Not a big difference. I don't know if you'd be asked to discriminate against those two. These rather disgusting photos here are of prismatic structure. They don't show up real well here. Perhaps that could be focused a little. But a prism, if you think about a prism, a multi-sided type unit where the length of the unit is longer than is the head of it, prismatic. And then columnar, what would columnar type structure be, just from the name? How would it be different from prismatic? Nice rounded top. I know most of you are high rollers, probably have columns out in front of your home, or perhaps out in the gate that you first enter to enter the family compound. You know what columns look like. Here's prismatic again. It's more angular. Prismatic and columnar structure are more evident as we move west and get into more arid regions. They're oftentimes associated with a high sodium or calcium, particularly calcium type environment. What are the benefits of structure? Why do we even care about it? Well, those of you that have seen some soil that was worked wet or seen some soil that was puddled will have an idea why we want good structure. We need good structure to promote good drainage. We need good structure for aeration, for gas exchange in the soil. We need good structure to promote good water use, allow rooting, and to get adequate germination. If you go into a no-till program and you have wet soils where you got some kind of coulter or other device making a seed opening, the soil's too wet, you're going to create structural problems right there that aren't going to allow for good closing. If you go in and till a wet soil, you're going to have big clods or big lumps, and other problems are going to give you a poor seed bed. So these are all things to keep in mind. If you get a puddled soil or one that's been worked too wet on the surface, you could impede drainage right from the surface of the soil. How can we affect structure? Tillage is very important in structural development, and when we get into the tillage section, I'll talk a fair amount about no-till in going into no-till from other types of tillage and what that might mean in terms of structural development, organic matter distribution, and these sort of things. Cropping systems, if we're in a system that includes a forage of some kind, we're going to tend to develop more of that granular structure. So the type of crop that we grow out there is going to somehow influence the type of structure it develops. The soil organisms, a lot of folks think a lot about earthworms, some don't think about them at all, but in general, not only the macro animals, the earthworms, etc., but even the soil microbes, the little small bacteria and so forth, and fungi are going to be working actively in a soil that's doing well, and they're going to have little exudates that are going to help to bind together the organic matter and the different particles that are there, the sand, silt, and clay, and that's what tends to lead towards that good structure. And finally, your drainage can influence it in the way that drainage is going to influence the amount of soil water. Got some citizens coming up the door hoping they can come in. I was just waving them in here to be part of this process. How can we use tillage to affect structure? One of the ways, of course, is to break up any kind of platy structure. Towards the end of my talk today, I'll talk a little bit about compaction, the different forms of compaction, different depths in the soil. But admittedly, we can have judicious use of tillage to try to aid us in areas that have become compacted before. Tillage is going to help in that it can allow good root growth. How does root growth help structure? It's kind of a thing that feeds on itself. If we get structural planes of development, blocky structure, where roots can go down, the roots now are putting organic matter down into the soil, and when those annual roots of crops slough off, they help promote and protect the structure that's already there. Tillage can be negative towards structure, and then if we go out on wet soils, we compact them. It's a pretty straightforward relationship. If we're on soils that are just slightly above or slightly below field capacity, with heavy equipment, we're going to push the air out and densify those soils. And no-till, again, I'll talk about this at some length later on, but no-till tends to promote aggregation of surface soils, but it is a process that takes time. Oftentimes, as we'll learn, if we first go into no-till out of a different type of tillage, we're going to get actually a more dense surface soil than we would if we came in and tilled that particular soil. How do cropping systems affect soil structure? You'll have some questions about this most likely. The cropping systems have an indirect effect based on a couple mechanisms. Number one, the type of cropping system is going to influence the type of root development, the root depth that you get. If we get increased root activity, we're going to have improved structure. That's how these forages work. That's how some of our grasses work in pastures. Tremendous amount of fibrous roots near the surface tends to develop this spheroidal or granular structure. Crops can also protect the integrity of the structure near the surface by providing a canopy. Once that canopy closes, the rainfall energy is going to be soaked up by the leaves that it hits, and we're going to tend to protect that structure we have. One of the benefits of no-till, of course, is the residue that's out on the soil has a protective effect on the granulated structure that may develop underneath. So it's just a covering mechanism. Cropping systems can add organic matter to our soils, particularly if we turn in part of our crop or manage our residue in such a way that we have organic matter near the surface. And finally, our cropping systems can influence structure by increasing the microbial activity like we get with the forages and grasses. How about soil organisms? And primarily what we're talking about here is earthworms. Earthworms are pretty good, I think, at taking crude organic matter and putting it through their bodies and exuding it out. What this does is tends to incorporate the organic matter in the upper horizon. Things get moved around. There's a couple kinds of earthworms. We get the night crawlers, which make vertical burrows, and kind of the red wigglers, some people would call them fishing worms, that tend to mill around all through there, incorporating organic matter, getting this stuff mixed in. They make old channels. These channels can be lined with organic matter, and again, they help break this material down. The microbes, though, are probably more important. And how do we have bad microbes or lack of microbes? We can kill them with poor water management. Almost any soil that the crop likes is going to be a soil where the microorganisms are also happy. What kind of conditions are they looking for? They want moist, they want warm, and they want gas exchange. These organisms and the crop roots are both going to give off carbon dioxide and require oxygen. So we need to have good structure to allow these gases to diffuse back and forth. One of the big problems with waterlogging is we cut this off and our oxygen supply disappears. It kills the microbes that are there oftentimes and also going to kill our crop roots. Other critters that we have are going to influence the what we call the macropores, or large holes, and these are going to be structural weaknesses that are going to be exploited by different crop roots as well. Where does organic matter come from? If we came here years ago before the prairie was broken out, we would see that there was a natural amount of organic matter there that had developed over thousands of years. What was the basis of this organic matter development? Well, number one, you need production of organic matter. You need to have something there, carbon fixed from the carbon dioxide of the atmosphere into plants, plants sloughing material off into the soil. That's where the organic matter comes from. Why do we have so much in this area? Who wants to distinguish themselves as a scholar again, like our mathematician did here earlier? Why was the organic matter preserved in this area through central Illinois and northern Illinois? That's right. Just got it back here. Why do I fake like someone answered? Yeah, good answer, good answer. The organic matter was protected because, well, let's back up a second. We got some folks who are a little bit older here. How many were here during the age of the dinosaurs? I can't see all the way in the back. What happened there? Well, how do we get our gas and oil reserves? Where'd that come from? Organic matter growing in a swamp, falls into the swamp and is protected from oxidation, right? Builds up over time. Well, what we have here is a shorter term example of that. The prairie grasses grew, they sloughed off, and the soils were mostly wet and cool, so they're protected from organic matter breakdown. Now what we have is drainage and tillage, which tends to break down the organic matter a little bit more. We still have some real nice dark soils, but they wouldn't be protected for all time. The sources of organic matter, primarily plant residues. Those people that are managing with livestock may add manure to the soil, which certainly is going to increase organic matter levels. And soil animals, and this would include, again, the microbes. They're always eating materials, dying off. This is part of the organic matter pool. And finally, some lucky communities have sewage sludge added to their soils, which again is a big source of organic matter. We hear a lot about humus. What that is, humus is simply the most resistant part of that organic matter which resists breakdown. You take your average plant, there's going to be a lot of material that's going to decompose fairly quickly. The lignins, the tougher materials, the waxes are what's going to be left behind, and that becomes part of the organic matter pool. What does humus affect in terms of your management for organic matter levels? Is it good, bad, or indifferent? Who wants more organic matter? Who wants less? Who could care less? That covers the majority of the group here. Okay. Organic matter is going to be a little bit of a source of nutrients. It's going to also influence the amount of herbicide that you need. In general, organic matter is a very good thing. That's why one of the reasons our soils are so good here in Illinois. What kind of effects does organic matter have in the soil? This is a difficult concept that I'd like to bring to your attention. Soil organic matter makes soils darker. Everyone upset with that idea? What color is organic matter after it's decomposed? Black, right? So, see if you can follow this idea. The more organic matter in the soil, the darker or lighter it's going to be. Darker. Okay, I'm trying to bring the group back here slowly. It's kind of like the lecturing equivalent of the shock paddles. Okay, soil color is darker. We have black soils where we have, say what, 3 to 5, maybe even 6% organic matter. How many of you have ever taken a vacation in southern Illinois, down below the Shelbyville Moraine? Got a few people. How many are aware that the state extends below Champaign? Okay. Next time you're taking a family vacation in southern Illinois, it's a tremendous thing. Just one other little faster vacation, some enjoyment. People are always looking for enjoyment when they're traveling with families. One thing you should really note and bring to the attention of the group you're with is when you drive over the edge of the terminal moraine in Shelbyville. This is a very inspirational moment if you approach it in the right way. This marks the lowest spot for the Wisconsin age glaciation. And you can view this right from your own family vehicle. Don't race out today and do this. I'm asking you to incorporate this into a trip that you're going to take at a later date. Point being, below this moraine is where we have what's called the old Illinoisan till plain. And the soils down there are much lighter. They do not have the kind of organic matter that we have in that moraine and back to the north. We get into some of the older soils that have been weathered more. They're kind of clay pan soils. They're lighter colored. They're lighter colored because they have less organic matter. So we get into some of these Sisney and Hoyleton and other soils down there. They're not going to be as rich and black as what we've got in this particular area. What does organic matter do for structure? Straightforward again. The more organic matter we have, the better shot we have at getting some granulation or aggregation of our different soil particles. And nutrients. Organic matter is a source of nutrient. And nitrogen, phosphorus, and sulfur all mineralize as organic matter breaks down. These different components are going to be released. Not enough to replace fertilizers in most cases, of course, but it is a source of nitrogen, a type of nutrient cycling that goes on with our organic matter pool that's in the soil. Just want to give you just a little bit of information on soil color. Now, we got it down pat, I think, that dark colors are related to organic matter. As we get browner, it means we have less organic matter. What are some of our gray colors? What are those going to be associated with? Clay, oftentimes. Usually they're going to be associated with limited drainage or limited aeration. What we're seeing here, there's two predominant forms of color expression in soil: iron and organic matter. Organic matter, the more it is, the darker it is. Iron is going to be in several different colors, ranging from gray to red. The gray indicates that there is not oxygen in the environment, which typically means there's water there. And what it does, it chemically reduces the iron. If you were to take a piece of iron and bury it where it couldn't get any oxygen, it would turn gray, become chemically reduced. That same iron, if it's allowed to stay wet and out where oxygen's available, is going to turn red. And that's simply the type of color that you're going to see expressed in the soils. Dark is organic matter. Light gray is usually reduced iron, limited drainage. Here's a nice dark soil, rich in organic matter. That's the kind of thing we can see around this area. No doubt where that particular color comes from. We move into some of the intermediate colors, and in fact, some of you that really want to take a close look at soils oftentimes notice little specks of gray or little pockets of red within a gray matrix. And what that really indicates is fluctuating water tables, areas where we're going to get times of reduction and oxidation throughout the year. And we get all of these different colors showing up. If we get really oxidized colors, of course, we're going to get the reds. So if you go down, how many have been, we had a limited number of people that have been south of Champaign. How many have continued on down and made a pilgrimage to Mississippi or Alabama and noticed some of the reddish orange soils down there? Maybe you've seen Gone with the Wind, or those of you who haven't traveled much, or have some kin there or something. No. Did any of you ever wonder what was below Champaign? I got a map of the United States I'll show you later. We'll brush up on some of this stuff. Anyway, there's the good red colors, and for those of you just jumping ahead, we're going to talk about different erosion types, and I bet you know some of this already. Would you consider us to be sheet, rill, or gully erosion? Some of you might have got that even without my help. Okay, we're moving into some real high-tech science now. Talk a little bit about the carbon-nitrogen ratio. And I think tomorrow Dr. Bob Hafe may talk a little bit about this as it interacts with nitrogen fertility in the soils. But the carbon-nitrogen ratio is pretty important. And what we've got is a titanic struggle in the soil for nitrate nitrogen in particular. We've got a growing crop and we have residue that needs to be decomposed. The residue decomposition is done by microbes. They require nitrate in their bodies to accomplish this. And so we oftentimes have a fight, which can result in disaster for a crop if there's too much carbon or carbonaceous material present in the soil, too much organic matter that's undecomposed. So the microbes compete for nitrogen. If we have a high, that's a phonetic spelling for high carbon sources, they can tie up nitrogen. So when we're dealing with residue, managing residue, or looking at soil amendments, we need to keep this carbon-nitrogen ratio in mind. It has to deal with our nitrogen management. CN ratio is simply the amount of carbon to the amount of nitrogen. You can do it in pounds or parts per million, however you're comfortable. In typical surface soils, we have about 10 times as much carbon as we do nitrogen. That's when things are basically in balance. We have a soil sitting out there now. If there's no residue on it, typically we're going to be in a 10-to-1 situation. Middle of the crop year, that's about where we're going to be at. Other materials that we might add to the soil have different carbon-nitrogen ratios to them. If we take a fresh legume like a clover, an alfalfa, a vetch, and turn that into the soil, it's got a little more carbon, but it also has some nitrogen in it. We're going to not quite have as low a CN ratio in that material as we would with the soil itself. So we're going to have a little extra added carbon to the soil if we turn that material in. Now, as we continue down this list and get into greater and greater carbon to nitrogen ratios, we are going to have potential nitrogen problems in our plant growth. And I know probably not too many of you are using sawdust in your operation, but sawdust now, this is a highly lignin-containing material, very difficult to decompose. It's difficult to decompose because of the high amount of carbon and low amount of nitrogen in there. If you were to go out, I don't recommend this, but if you were to go out and turn in a bunch of sawdust and plant corn and do your normal operation, you would see some yellow corn. Because the microbes are going to outcompete the corn plant for the nitrate nitrogen in that soil so that they can get that sawdust broken down. So that's what happens. You put a high carbon material in, zoom, the nitrate is taken up and you can run into problems. If you had a bunch of wheat stalks or perhaps some corn stalks in and you're coming back with corn again, you turn those things in, there's going to be some competition for the nitrogen that you put out with that crop. Microbes versus the corn plant that you've planted, okay? So that's a little bit of a problem. That's why many times our crop rotation is so good, because the soybean can get its own nitrogen while the different residues are breaking down. What about green manures? This isn't used a lot in this area, but nationally there are some areas where green manures are used. Green manure is simply referring to the idea of a cover crop. Plowing that cover crop in. Some people that are working with no-till don't really turn it in. It's not really green manuring, just using a cover crop as a thing to protect the soil during the winter and then planting directly into that after it's been killed. Advantages of green manuring or a cover crop, you can get reduced nitrogen leaching. This is primarily an East Coast thing and a southeastern United States thing where they plant rye and try to get nitrate nitrogen trapped in that rye crop rather than leaching through the sand in the winter. Then they kill the rye crop or turn it in and it's released back to the subsequent crop. Soil erosion protection, that's a more concern here, I'd say, and a good use of these different cover crops. Particularly a rye, a grass crop that's going to provide a good cover coming into the winter. It'll help break down the energy of the rainfall. In theory, we can get nitrogen release for the next crop. I've fiddled around a little bit with a vetch crop down in Havana, Illinois on a research facility we call the Sand Farm. Growing vetch after the soybeans, growing your own nitrogen, killing it, and allowing the corn to use it. Had some success there. Not going to be a real tremendous feature for the northern part of the U.S. because we have problems getting it established and growing enough nitrogen before the subsequent crop. Here's what this rye looks like, and again, early in the spring or late in the fall, if you get this kind of cover, you're going to get some erosion protection. And later on, this good-looking guy works for University of Illinois in the southern part of the state. For those of you who have already indicated you've not been south of Champaign, he's measuring a rye crop, and this can be a very aggressive cover crop. and killed, and there's some unique management things that need to be taken into consideration when we use a rye crop ahead of soybeans. I'll talk about those disadvantages, potential disadvantages in just a minute. The other crop is a hairy vetch, a very lush, beautiful crop, contains a lot of readily broken down nitrogen, as evidenced by the lower C/N ratio than other materials might have. So that's going to release some N. What are the disadvantages? A big one, I did a little bit of research with some other folks at the U of I in 1988, and those of you that were in the business at that time remember that as a dry year. If you have a cover crop growing and you have plans to kill that, and you kill that and the rains don't come, you probably have a depleted soil profile where the moisture is gone. And so you've automatically put yourself in a drought condition. That's a big potential disadvantage. I suppose I should say, in fairness, it's an advantage if you have an extremely wet year. In, say, in southern Illinois, and you allow that crop to pump the water out of the soil, then kill it with Roundup and come in and plant soybeans. There's a greater cost involved with using a cover crop because you oftentimes have an unused crop, a crop that you're simply using to establish your next one. And it's a home for insects and animals, and I think Kevin Steffi mentioned this a little bit, coming into grasses. If you've got acres and acres of bare land and one nice green trap crop, a lot of these moths are going to come in there and find that to be a nice place to start a little family and eat your corn as it comes up. Okay, that about wraps up the first section. Any questions, any burning questions in that particular section? If not, we'll move right along. Boy, what an attentive group. This is almost exhilarating to be able to talk to a group like this. Let's talk a little bit about soil water. In this particular section, I'm going to focus on drainage a little bit, talk a lot to you about plant available water, how soils hold water, how water moves through soils, and finally the cropping system effects on soil water. Drainage is a very important part of agriculture throughout the Corn Belt. Most of our soils, or many of our soils, were poorly or somewhat poorly drained as we came in and broke these areas out. And it's important for us to get the saturation zone lowered so we can get good rooting going on in these soils. Texture is a big influence on the amount of drainage we get. Obviously, all other things being equal, a sand is going to be better drained than is a clay. The more clay we have, the less the chances for slower infiltration, less permeability moving through the soil profile. Soil structure is going to have a big influence. Some of our clayey soils actually have such good structure that the drainage is fairly decent internally. And the type of drainage we have internally is going to, in large part, determine whether we use a surface or subsurface drainage system. I'll talk about that in a couple slides. Impermeable layers, again, getting back to southern Illinois, they talk about a clay pan soil down there. And what you've got is a layer that's formed that has virtually no pore space in it to speak of. And the water just sits up on top of that, and it's very slow draining. And finally, water table levels. If you have a backed up river, or your drains, tile drains are plugged, or you have a naturally high water table with no outlet, you're not going to have very good drainage in that soil no matter what you do. Surface drainage is used most likely on impermeable soils. That means soils that have poor internal drainage. Why is surface drainage used in these cases rather than subsurface? If we were to design a tile system for a soil with poor permeability, very poor permeability, we would have to put the drain tiles in 40 or 50 feet apart, and the expense of that is prohibitive. We might be able to get it to work, but we'd have to put them very shallow and very close together to get these systems to work, so it's too expensive. So when we look at surface drainage, this often involves land grading. We need slight slopes. We take the water to a common collection point and run it out off the field through different ditches and waterways. And again, this is going to be more prevalent in southern Illinois than it is in this particular area. The soils that look like this, they're kind of whitish surface soils. Again, 1 to 2% organic matter. They got a clay pan down about 12 to 18 inches, and the water just sits there. A lot of the water loss off these soils during the crop season is due to evaporation rather than percolation or drainage away. So they get a big rain on these soils, they've got some serious problems. And they oftentimes get in very late planting because of that. Subsurface drainage is going to be used on our darker soils that have good internal drainage. So the biggest problem, the reason we had so much water in this area is simply it's low-lying land and we have a water table there. We can whisk it off in many cases through drainage systems and get it into some of our drainage ditches and then off to rivers and get rid of it in that way. So we need permeable soils. You drain the soil deeper. What's our depth of, typical depth of installing tile? 3-4 feet. That's typically what you're going to see. In some cases 2.5, rarely deeper than 4. You run it into a main field tile. I don't have exciting pictures of this, but there are 2 types of drainage systems you may be asked about in your CCA exam. One would be a parallel system, and one would be a herringbone system. Even without benefit of showing an installation of one of these systems, do you think you could recognize them? What would be the attributes you would look for in a parallel drainage system? They would be parallel. Very good. The drain tile would be parallel. How did you know that? No, you figured that out, didn't you, right here? Very good. Now how about a herringbone? How would they look like? They would look like a herringbone. This guy's got it all figured out down here. So your parallel system is parallel running into mains, and a herringbone is like a herringbone. I know a herring is probably not a fish that typically runs up into these parts. You're probably more familiar with in terms of eating delicacies of buffalo or carp or something like that, but just trust me when I tell you the herringbone comes in at an angle like that. Boy, it makes me hungry just thinking about that. And boy, a nice scored buffalo carp sandwich would be good right about now. Especially, you know, if you really luck out and get the blood vein in there to get that extra taste, that's always a good thing. Okay, here's what our subsurface system looks like. And again, this is installed on some of the lighter soils, which typically would have surface. And I show you here that you have to put these things 18 to 20 inches rather than nice 3.5 or 4 feet that we can get in these darker soils. Talk a little bit about plant available water. This is one of the great mysteries of nature, and I know this group will be excited to learn about some of this stuff. We have water that comes into our soil, and the crop uses it, and that may be the extent of what we know about it this time. But what I'd like to do now is tell you how the soil holds it, why the plants pump it out, and where we can tell something about our soils in terms of how much water they hold. Plant available water is a strong function of soil texture. Which soil holds more water for a plant, a sand or a silt loam? Silt loam, right? The reason that this group is so affluent, well-educated, living in nice homes is in part due to your skill, in part due to your education, and also by the good fortune that you've landed up on these nice dark soils. These are the best soils in the world, bar none. And the reason is because of the depth, the rooting depth that's involved. The soil water holding capacity is almost unrivaled. That is, the amount of water that the soil can give up to a crop during a year is higher than it is anywhere else in the world. You combine that with the type of rainfall that we get around this area typically, you're on your way to producing a great crop. Any guess inches of water that a corn crop uses in a year in its growing cycle? How many inches of water do we need for that crop to grow? 20? 22, 24, somewhere in that range. How many inches of rainfall do we get between, say, May 1st and August? It's variable, yeah, I will grant you that. We've had guesses there from 0 to, what, 30? Well, it depends on the year, but in general, we're going to get, oh, I don't know, 12, 15 inches, something like that. And if we get that in a timely fashion, and we combine it with the soil water that's already stored in that soil profile coming out of the winter, we're on our way again to making a pretty good crop. We're going to talk about a couple points called the field capacity and the wilting point, and show you how, given those 2 points, you can find out how much soil water is held for crop use.